Good evening to all of you. Today's lesson is going to be reliability, prediction methods. We already saw prediction methods. Data is given, parametric, non-parametric analysis. There is only one way for which you need data. In parametric and non-parametric method, we need data to be either plotted or to be either viable analysis or non-parametric method. You arrange them in a certain format and see what is failure rate, etc., etc. You already seen one method, but that is you have the data about the equipment. But this is prediction method is when you don't have the data about the equipment, you are just asked to design maybe a lathe, maybe an electronic component. What do you do? How do you start with? Somewhere you have to start. The data is not available, so I do not know what is going to be the reliability. So how do we do this? This is a starting point for anything where for me data is not available. So we will see how to do this. A very fairly simple module. May not even go for half an hour. So with this we'll complete the reliability topic as a whole. Some bits here and there may be left, so I will do it when I come back. So we are going to see how to start a thing. For example, I'll take two examples. One is you have got an electronic board. What happened to this? You've got an electronic board, PCB, printed circuit board. It has got all components fixed. Transistors, resistors, capacitors, inductors, diodes, many components, coils, they are all fixed. I give power supply to this, it is supposed to give certain output. So this is the module. This is a basic unit of, like this I manufacture many modules and I put it in system, then I make it in a box and say, okay, this is my electronic instrument or entire equipment. So the basic module is a printed circuit board. So in a board like this, I know components it's populated with components. This much only I know. And I know what are the components. I know what components. Second thing, I know how many components are there. Just count. You don't have to know about the functions. Yes. You may be a civil engineer doing this, you may be a mechanical engineer doing this, so you don't worry about the functions, how the diode works, how the capacitor works. It's not your concern. But you have to only simply count the number of components. How many are there? So the process here we apply is, we apply certain mathematical data, mathematical model, based on which is the past data people have collected and documented. If I take a capacitor, what is the reliability of a capacitor or the lambda of a capacitor? I don't know, because I'm just designing with a capacitor. I don't know the lambda, the reliability, and the failure rate. I have no idea. If I make the equipment, I run it, I conduct failure test, I will find, okay, this capacitor fails so many times in so much of time, so I get the failure rate. But now I'm designing, I don't know anything. So how do I do this? How do I get it? So basically, it is prediction for each component, which is in the PCB. Methods. There are three methods of doing it. One is the purely empirical method. This is failure of component. The second is the physics of the failure. Here is where the root cause and failure mechanism. And the third method is live testing. This we have seen in elaborate manner. Make the equipment subject to test, take the failures, sensor data, uncensored data, empirical method, parametric method, all those things we have seen it. Physics of failure is, so if they take a capacitor, how does it fail? Or you take a spring, how does it fail? You study what is the probability of failing. What is the probability of spring, for example? It fails under due to fatigue, due to fracture, due to the component failure, how it fails, what is the probability of failing. So using all these models, you get the failure data. So this we have done. This we are not going to do. It's not relevant for us now. This is for research. So I am only going to now simple empirical method. This is what we are going to see. If you can, see, you should be very careful and you should tell in an interview about prediction methods. There's nothing wrong in saying that I know only empirical method. So that is what is widely followed in the industry. Then I know live testing. You don't have to worry about, you don't have to feel guilty that you do not know physics of failure because we are not research students. So we are going to be practicing engineers. So what is required for us, you know, nothing wrong in telling that. Right. Now, where do I get this data? When I have empirical methods, so our emphasis today's class will be all on empirical method. Empirical means no big mathematics. I just simply pick up the data from somewhere. So the data origin or the data is available. What is called? One is the military handbook 2167. This is for, I'm talking about for electronic equipment. I will come to the mechanical and the second part of this lecture. Electronic equipment. You have military handbook 217. She's got two versions, I think. Version 1 and 2, which is the latest, I don't know. But you get in the internet, these things are available. There's nothing to. This is the military application. In the civil side, you have the cell core, stroke, telcardia. This is also a handbook. Then the SAE for automobile. The automobile electronics part. Then there is, Chinese will have everything of their own version. It's called China 299B. So many handbooks are available. They are available in the market, but the most popular one used is this. Everybody uses this. It's an American version, handbook. Everybody invariably in the industry use this only. The second is this second. All others I'm just telling for completeness, but if you can able to refer to this or this, you'll be able to do your job. So the data is just lying there in the handbook. So what is the method? Now I know where the source of data is. Handbook is available. So I take the handbook. And how do I proceed? This empirical method consists of two parts. Two parts. One is parts count. Two is part stress. Actually, two parts. It's not two methods, man. There are two parts, two steps. Step one, I do this. Step two, I do this. There are two steps of doing this. Steps. Doing this prediction using the data handbook. Now, what is the first step? First step is part count. I said I have the printed board. I have populated this with components. So in this step, I have to only say that I have got n parts. N can be any number, hundreds of numbers. Now, what is the model behind this? The model behind this is that if any equipment fails, that means all these 100 parts are in series. Electronically, they will be connected to anything else. We are not bothered about it. They are all in series. That means any one component fails, this board fails. Fair enough. Otherwise, there is no reason to be. There is no reason for this component to be in the board. If the component fails, it has to have an effect. Otherwise, why will I put it there? Wasting money. So if the component fails, the board fails. So that means all the components are assumed to be in series, which is a very valid assumption. Nothing to say this assumption is wrong. Otherwise, there is no business for the component to be in the board. So all the components are in series. So what you do, lambda for the board as a whole will be lambda 1 plus lambda 2 plus lambda 3 plus lambda n. So individual components lambda failure rate, if I know, I get the lambda for the board. Thank you. So if I get the lambda for the board, then the reliability of the board is e power minus lambda t. So from there you get all of, and f of t failure rate will be 1 minus r of t. And the differentiation of this is the small f of t. So all those things you know. You can do it. So basically I have to find lambda. This is nothing but sum of the lambdas of this. How did we get some of these? Because they are in series. Yesterday also I told you e power minus lambda 1 and t, e power minus lambda 2t, etc. e power minus lambda n t equal to the total reliability. So this is nothing but e power minus lambda t equal to, if you put lambda equal to lambda 1, lambda 2, lambda 3, lambda n. So this is the principle involved. It's nothing more than this. Now, how does the data given in the, I'll give you some reference also, you can see it later. So what the handbook gives is, what they call first is, so you may use your device, a component. person A will use it, our application A will use it in 20 degrees centigrade, no vibration. Application B may use it at 50 degrees centigrade, vibration. Person C may use 50 degrees centigrade, no vibration, but excess voltage. So like this I will use in different, that means these are all the environments in which it will be used. Now for the same component, I can't give so much of data, so much environment will be there, variations in environment. So for each combination, I have to give one lambda for each one environment condition, which is very difficult. So the handbook gives what is called as a reference lambda reference. The reference will be what? Standard operating conditions, correct voltage. If it is 12 volts DC, you apply correct voltage, no vibration. So a specified environment conditions are assumed and the component is given lambda reference in the handbook. So handbook first starts with the reference lambda for a specified conditions. Once I do that, once this is available, then the handbook gives, but you want for your own condition, not for standard condition. So what do you do? So you simply apply some correction factors to find what will be the lambda for you. The handbook also says how do you apply the correction factor and what are the correction factors. The beauty of the handbook is it also gives what is the correction factor. So the final lambda will be equal to, but each one component I am checking, just for one component, the value which you have to use is lambda reference, which is given for a standard condition in the handbook, multiplied by, there are factors called the pi factors, which is given in the handbook. So it will give your reference value, that is the standard environmental conditions, and it will also give a set of a large number of pi factors, 50 degrees, 70 degrees, vibration this much, this much, voltage variation this much. So it will give for each one of these environment condition a factor which is called a pi factor. So you have to take the reference lambda multiplied with the pi factors, you will get a lambda for the component. Then the lambda for the board will be sum of this lambda what you got. For one component I got up to 1 to n. What is the sum? This will be the lambda or the failure rate for the board. That is fairly simple so far, isn't it? The pi factors example. So that means it will look like something like lambda for one component equal to the lambda reference for that component. Some people call it the base value. In some, I think, the lambda base. Base means standard conditions, standard environment conditions multiplied by pi factor S multiplied by pi factor T multiplied by pi factor E multiplied by pi factor Q multiplied by pi factor A is given in the textbook, in the handbook. What is the pi factor? Yes, stress factor. The voltage stress, depending on what is the voltage you apply. Pi factor T, you could have guessed it. It is a temperature factor. And pi factor Q, quality factor. So who manufactures this capacitor or the device? If it is company X, Motorola, yes, maybe good quality. Somebody else, some Chinese thing, may not be a good factor. So it gives a quality factor. Pi factor A is some adjustment factor. Mind you, you don't have to guess any of these things. All these are available in tabulation form. The tabulation is there in the handbook. Here the device is given, capacitor. So it gives, this is pi H, this is pi T, this is pi Q, this is pi A, or any other factor. They are all mentioned here. 1, 1.5, 0.5, 1.8. These factors are mentioned. So you have to only put those figures, take these figures from the table, put it into this equation, and the reference is also given. It will be the lambda reference, or lambda B is given. So you put all those things and find your lambda factor. Then there may be for transistor. Now the only difference for so many devices are there. For example, we are dealing with electronics. There are many devices are there. Each device, for example, you have got microcircuit, you have got memories, memory chips, what are digital devices, gates, you got diode, you have got connectors. Please don't forget about the connectors. So for everything, it is there. The only difference is for capacitor, the whatever equation I have given, it may be like that. For diode, I take lambda for a diode. The lambda reference will be there, and this equation will be something different. Maybe pi A plus pi B. It may not be pi A into pi B, or it may be pi A plus pi B into pi Q. So this format will be different. In other words, the generalized equation will be a reference lambda given in the book into a function of various factors, the pi factors. It can be all multiplication, it can be summation, it can be anything, but it will be given. This equation is given in the handbook. You don't have to guess any equation. If I go for a diode, first it will say, please use this equation. Then it will say, look for lambda reference. Then it will say, look for the factors. And you put it, so lambda diode you got. So you got lambda capacitor from the book, lambda diode for the book. Then you get the lambda memory from the book. So for every component from the book, you get the lambdas. And once you get the lambda, all you have to do is simply sigma of the lambdas, component from 1 to n. Remember, in electronic circuits, PCBs, components will be in hundreds, not 1, 2, 3. So you put all of them, 100 number you add, failure rates, you get the total failure rate of the thing. And once you get the total failure rate, then I have to put, this is the lambda component. Then the reliability of that board will be e to the power of minus lambda of that component into the mission or duration time. So I got the, so now one board I got the reliability, the second board I get reliability, the third I get So this is board 1. If I take, see if there is n board in the thing, so Rn of t equal to R1 of t into R2 of t board, R3 of t, like this. So from the component, I come to the board. From the board, I go to the system. This is how you start your design. Once you start and say that cycle I told you day before yesterday, I think class, start with something, design, see whether it meets the requirement assigned, apportioned to each of these. If it doesn't meet, go and look into the components, look for a better component, a better pi factor, which has got a better reliability, then change the component. Like this, you have to do an iteration process, keep on doing it till you get the thing. And if you don't get it, then you go for standby, redundancy, things like that. How do you verify your design is right? You manufacture a prototype, subject to test. Testing methods we saw. You test up to time t, note down the failures, or test up to r number of failures will occur. Total time you know, failures you know, failure rate you know. So that failure rate and what you have predicted, if they are same, fine. If they are not same, obviously there is some mistake. So you look into again the design, which component is failing, whether the data has been correctly taken out or not, what is the mistake. So this is how you start your design and verify your design and then finally finalize it. Okay, this board is now okay, it can go for production and commercial use. So this so far I have been talking about electronic products. So you may ask, electronics is not the world. So you do have mechanical and parts also. Many things are mechanical. So how do I do this? So reliability prediction for mechanical equipment. Similar to that, the method is exactly the same. Similar to that, you have a handbook. Yeah, before I come to this, I would like you to do one reading of, I'll give you one this electronic thing. I will give you one book. I give you very small worked out examples, how to look at the table, how to do it. You go to the website, Moog, small m, small o, moog.com. It's about 2 pages or 3 pages, some few pages. So some examples are worked out in this, guiding you how to proceed, how to get the lambda for the product, how to get it. So if you go to this website, it's a nice reading, simple layman's reading, you will know the prediction method. So mechanical equipment we will see now. But this also, handbooks are available. One such handbook is by the, one such handbook is by the US Navy. Again, it's all military based. It is they who have done the pioneering work in all this, painstakingly collect the data, formulate it, examine it, everything. It's they who have done it. The reference is, you can see in the web available. Sorry. NAV start dot mil. Navc dot navy dot mil handbook. This give you in good, in simple English, how to use the data, what are the equipment for each equipment, how to do this. But in mechanical, unlike the electronic, the data is very limited. Electronics produced in mass numbers, so there is huge amount of data. So it is, whereas mechanical, it is a little difficult. But they have collected all those things. In spite of all the difficulties, they have collected all those data. So here again, what they do, the product for any assembly, the final thing will be the lambda base into some, they don't call it pi factor, they use the word C, I don't know why. CQ into CF into CV into CN into CS into CDT into CSW, etc. The many factors the book gives in this format. As again, as like the electronic equipment, for some it may be lambda base into, this may be CP into CQ divided by CS plus Cn. So it will be a function of the C factors. In other words, it will be a function of the factors here and the lambda base. The base lambda also will be given to you. These function factors are also given to you. What is the function expression is also given to you in the handbook. But only pick up the values, the tabulation is there. Pick the values, put it into this equation, you get the product. That component. Now, what are the components possible in mechanical? Now, I will see. Sorry, this. What are the C values? For example, CP, for example, I am giving is a multiplication factor. Multiplication factor, which considers the effect of fluid pressure. This is a component used in valve or something like that, like a poppet. So it depends on the failure, depends on the fuel pressure. Fuel pressure is less, naturally the component will fail less. If pressure is very high, it will go. Then CQ, again a factor for leakage. CV, what is the viscosity of the fluid? So it is all mechanical properties of the environment. So the base is there by a given normal environment, then different environments in which you put into use. So that you apply a correction factor and find the component failure rate. Now this book, if you look at it, it has data for seal assembly, the mechanical part, gaskets, again a mechanical part, springs, mechanical part, solenoids, electromechanical part, contactors, electromechanical part, valve assemblies, pumps, brakes, clutches.
So the screen is not coming.
Gone. Gone?
Yeah, after valve assembly, it didn't come.
Okay, should I send the new invite again?
1 second, let me just refresh.
Compressors.
So can you send the invite again?
Yeah, I'll do it. One second, the board here itself is gone, that is a problem.
Oh.
Yeah, send it.
Yes, sir. Ready.
Got it?
Yes, sir.
So like this, any mechanical part, filters, fluid filters, electric motors, couplings, mechanical couplings, shaft, driving shafts, belt, conveyor, even it gives even for fluid conductors. What is a fluid conductor? Just a pipeline. It's got couplers, assembly, how the pipe gets corroded, how do I find out the lambda for the pipe. So if you do this, so you think of anything in mechanical, it is there in the book. So you just take that book, use the reference value. So it is available, you can download and read it, no problem. So you can decide now for the components. Component you got. Same, assume that a machine has got whatever part you have chosen. All the parts will be in series. One of them fails, the machine will fail. So put the component. R of T, the reliability of the machine will be e power minus lambda into T. Lambda equal to the sum of all these things. Components. So here is an exercise where you don't have to remember anything. You should know there is a handbook available, like mill handbook or for electronics, naval handbook or mill handbook also is there. I'm told about military handbook as well. Components. So go to those handbooks, pick up the values, reference value, parameters, multiply the reference value by parameters, you get the component value. Sum of the components, you add all the lambdas, you get the equipment lambda. And once you get the equipment lambda, you are done with it. Then the company wants to verify it, you manufacture a prototype, subject to test, run it for so many times, so many hours. How many failures fails, filter fails, pipeline fails, solenoid fails. Check down the failure data. We know how to analyze the failure data, see whether it is same as what you have predicted. If not, look at which is the component which is contributing more. And maybe you got to look for a different component. Maybe it is not been manufactured properly. Maybe it has not been seated properly. So you can do all those analysis. And then you can say, okay, it is now matching my design. I'm satisfied. It can go for commercial production. So this is the starting point. So as I said, I've started this series of lectures with the end. End was what? How to do a metro analysis. Even without with slight knowledge of what is mean time between failures and things like that, and went through. I'm ending the series with the starting point, which is how to get the failure rate of a component without knowing anything about the component, but only knowing where the data is available. So in the actual design process, it will be the reverse. You take the component, you take the lambda, do the design, then test it, then verify it, satisfy that, then you go to that, use it in the system, use it in the metro or wherever it is, then look for what is the punctuality or the reliability of the system or the equipment. So this is the whole process now in the loop. I think I have covered everything. With this, we stop the reliability. The only pending items are, I said that in the censored data, I said that I'll come back and discuss with you, because there are certain how to adjust the ranks of the censored data. There is the ranking 1, 2, 3, 4. It will not be 1, 2, 3, 4 when it is censored. It will be 1, 2.5, 3.4, 4, like that. How do you get these figures 2.4, 3. How do you adjust the rank adjustment? It's not very important, it's not difficult, but needs a heavy interaction between you and me, so that we can come to the conclusion how to you get the figures. So that I will discuss when I am in the class. Then of course I'll work out the set of questions. I will work out and give it to you. A pool of questions which will prepare you for your interview as well as for your exam, whichever exam. And I am sure that with this knowledge and with a little bit of your own work about engineering statistics, the basics of engineering statistics, like histograms, then the errors, standard deviation, things like that. If you can learn, I am sure you can appear for your CRE exam as and when the time is due. I prepared you enough on these things. Now only maintainability, Mr. Paul will come and talk to you. Availability I have already talked, because availability is only MTTR values will be given. You have to only by previous projects and things like that, you take MTTR values. A lot of data available. MTBF we have talked very much in detail. So availability is as good as the once you know the reliability and this you can get it. Maintainability, yes, it is a separate entity itself. There are certain aspects which you have to keep in mind, mostly theoretical. Maintainability is nothing but how to reduce the MTTR. Anybody would like to keep a less MTTR so that availability is very high. Mean time to repair. How to reduce the mean time to repair is the basic thrust on maintainability. What are the various methods of maintenance which will lead to minimum MTTR? The component should be accessible. I must have sufficient stores. I must locate the stores in such that I pick up the store and travel to the equipment. That point is minimum. So these are the things. How much store I will keep, at what distance. Then preventive maintenance I do for inspection. At what intervals do I inspect? Once a week, once in 10 days, once a month. What is the optimum period of inspection, which will give me the low cost? So these are some of the quality factors which will be taught in maintainability, which Paul will maybe a few classes will ask him to take. So he will do that. With that, next topic I will do is the last syllable of RAMS, that is S, that is safety. So from tomorrow onwards, we will start introduction of safety. But if Vinay, if you can send me a mail,
yes sir.
What are the things Sudhir have covered?
Yes sir, I'll mail it to you.
You said send me a mail so that accordingly I'll adjust. I don't want to repeat the same thing again.
Yeah, I'll mail it to you.
What is so I will only says basically I intend to teach the safety basics.
Yeah.
Quantification of safety. How do you quantify safety?
Okay sir.
In equation forms, simple equation forms.
Okay.
That's what I wanted, but I would like to know what Sudhir has started.
Okay.
Take it. Okay, right.
Yeah.
I'm signing off.
Sir, there is a suggestion if we can start the safety sessions from Monday.
Monday, yeah.
Yes,
Why again they want 1 day rest?
The last there.
Why? Tomorrow there is a bandh or what?
I'll not give you next week. You have to give me. Why we should?
What is the reason for it?
There is one day break. So this
One day break.
this Sunday also Sudhir sir is taking 3 hours. So
Oh, I see. Sunday Sudhir is taking, is
yes,
it?
sir. His visit to Bombay is postponed. So he said
Uh-huh.
I'll finish little more and then go.
Okay, good.
Yeah.
Okay. Then I'll start on Monday.
Yeah. Okay, sir.
Safety, I will have maybe 5 classes, not more than that.
Okay, sir.
Because it all depends what Sudhir has completed.
Yeah. I'll
So
mail you
give me
the. Yeah. I'll mail it to you
send me
right away after this.
Ah,
Yeah.
okay.
I'll do that.
Okay, right. So Monday evening or Monday morning for me,
Yeah.
I will start
Okay,
the
sir.
safety.
Okay.
Right.
Bye, sir.